For those of you who missed the game, I thought I'd go through the notes with you just so you kind of understood what was happening with average rate of change. Average rate of change is the same thing as slope. So that's a key idea. Slope and average rate of change are basically the same thing. The only difference is that slope is constant, right? That's we use it with linear equations, and average rate of change, we could use it for any function. So hopefully last year you did learn your slope formula, like y2 minus y1 divided by x2 minus x1. But if you wanted to get fancy, we could even use function notation, because we know f of x2 is the same thing as saying like y2. F of x is the same as y. So that's just good for you to kind of have the heads up. As you're thinking about average rate of change or calculating slope, more often than not, if you have a photo, you're likely going to just start counting the boxes. So I'm going to start by just using the picture down here, but you're just going to say, okay, to get from here, this point to this point, I'm going down 1, 2, 3, 4 boxes. So I'm going down 4, that's a negative 4. And I'm going over 1, 2, 3, 4 boxes. I'm going over 4 boxes. So my slope is negative 4 over 4. Remember that's your rise over your run, and that equals negative 1. Great. I want to show you that whether you use the picture and you count the boxes or whether you use this equation, it's exactly the same. So I have my points negative 2, 3, and 2, negative 1. And if I label them with x1, y1, keep your 1's together, and x2, y2, keep your 2's together, but it doesn't matter which one you label x1, y1, or which one you label x2, y2. Now we're just plugging in our formula. So we're saying y2 is negative 1 minus y1 is 3, divided by x2 is 2 minus x1 is negative 2. Well, negative 1 minus 3 is negative 4. When I do negative 2 minus a negative 2, subtracting a negative is like adding, so it's a positive 4, so that also equals negative 1. So we can see whether we use a graph or our equation, we get negative 1 as our slope or our average rate of change anywhere between those 2 points. However, in most cases, it's not realistic to travel at a constant speed for an entire trip. So what we have going down below is we've got this bike ride. And as Sasha's bike riding, she's not always going exactly the same speed. Like maybe she hits a hill or she's going downhill. She's going to go different speeds at different times. So that's why we talk about calculating the average rate of change. Overall, during this interval of time, what was she doing on average? You can think of the average rate of change as the slope of an imaginary line between 2 points, specified points of a function. Calculating the average rate of change is the same thing as calculating the slope. So like even if I had some funky graph, like let's say it looked like this, if I choose any 2 points in my graph, I'm just saying what's the slope between those 2 points. It may not even be where the graph exactly is, but it's just talking about where overall, if we average all the little bitty slopes, what is it doing it? Okay, so if I had this graph where the average rate of change is not the same between any 2 points, because you'll notice it kind of starts up steeper and then goes a little less steep, etc., that we will have to look at specific intervals to find the average rate of change on. So this first one asks us between 7 and 15. You could either count on the graph, although I will say this graph is not the most accurate or the best, sorry, I apologize about that, or you could use your formula. On this first one, I'll just count. So we'll say, how much am I going up by? Well, I'm going up by 2 boxes, and how much am I going over by? I'm going over 8. So my slope using rise over run is 2 over 8, or 1/4, or if you prefer decimal, 0.25. Any of those answers are equivalent. Let's go ahead and look at the next interval. If I say between 15 and 44, okay, maybe on this one I'm like, let's use an equation. So if I use an equation in here, we're going to go ahead and be like, okay, which one do you want to label x1, y1? Maybe I say that these ones are x1, y1, x2, y2. And let's say, okay, we're subtracting our y values. We're saying 23 minus 10. Divided by what are my x values? Well, my x value, what matches the 23 is my 44 minus 15. So that's 13 over 29, I believe. And I think your decimal is like 0.45. But you're definitely going to have to check that because I don't have my calculator right next to me. Okay, so now which interval has the greatest average rate of change? If we're just comparing these two, then we would say the interval of x to 15 to x equals 44, this is definitely greater. It's a bigger number. However, if you want to think about it more graphically, since this graph is not the best, kind of drawn scale-wise, think about a graph like this. If I labeled these three parts as like A, B, and then C, which part of the graph would have the greatest average rate of change? You're looking for which part is the steepest, which I probably could have done this a little better, but I was thinking C was going to be the steepest, but A is also looking pretty similar. So you're looking for something that is the steepest. And I think that's a key idea as well, that as you look at a graph, that something that's the steepest is going to have the greatest average rate of change, meaning it is increasing the fastest. Okay, as we look at the second page, I could also ask you to do average rate of change from an equation and from a table. From an equation, I will tell you right now, this is not the equation that represents average rate of change. We're just saying this is some function. This actually makes that U shape, which we call a parabola, and you'll study more next year. But we're saying, okay, if I was to graph this, or if I give you the equation, what's the average rate of change between, on the interval 1 to 3? And when we say 1 to 3, we're talking about x values. Everything in this unit, our interval is x values except for range. So we're saying from x equals 1 to x equals 3. So there's two ways you could do this. I think one way you could do it is you could do like f of 1, and then you can say, what's 1 squared plus 3? 1 squared is 1 plus 3 gives me 4. And then I could do the same thing with f of 3. F of 3 is saying 3 squared plus 3. 3 squared is 9 plus 3 gives me 12. Or if you like using your calculator, you could plug this equation into y equals and look at your table of values to find the ordered pair 1, 4, and 3, 12. Now that we have those points, we're saying, okay, to find average rate of change, same thing as slope, we're subtracting our y values. So we're saying, okay, if I subtract these, maybe I start with 4 this time, minus 12. If I start with 4, though, I've got to do the 1 that matches it. So I've got to put 1 right below it, and then I've got to subtract 3, because the 12 goes with the 3, so they're on top of each other. 4 goes with the 1, they're on top of each other. So then I get negative 8 over negative 2, which gives me 4. That's the same way you'll find out if you switched it and did 12 first. You'd also get an average rate of change, or a slope between those 2 points of 4. Okay, our next one. So now we've got this exponential function, and we're saying, what's the average rate of change between 0 and 3? I want to point out, with any exponential function, the average rate of change will be different between 2 points, because in this part with growth, it is increasing at an increasing rate. So the slope is definitely not constant. So if I say, what's g of 0? We're saying, okay, 4 times 2 to the 0, well, that equals 4. G of 3, well, we're saying 4 times 2 to the third. 2 to the third is 8 times 4 is 32. So now you pick. Maybe I'm like, okay, I'm going to start with my bigger number this time. So I'm like 32 minus 4. Those are my two y values. That's your y's, the change in y. Divided by my change in x's, well, 32 pairs up with 3. So I'm doing 3 minus 0. So 32 minus 4 gives me 28, divided by 3. I would probably leave it like that. If you like fractions, then I believe that's like 8 point, is that right? 9.3 repeating, sorry. That would be fine as well. Okay, two last examples. The two last examples come from a table. It's still that same equation that we were using on our front page. We're still thinking about the change in our y values divided by the change in our x values. The only thing here is you got to find the points from the table. So if I say from 2 to 6, we're saying, okay, we're starting here. We're ending with my x value being 2, ending with my x value being 6. So make sure you circle your 2 right points. And now we're just doing the change in y over the change in x's. So if I start with 9, I'm like 9 minus 3 is my change in my y values. If I start with 9, I got to start with 2, the x value that goes along with it. So I'm doing 2 minus 6. 9 minus 3 is a 6. 2 minus 6 is negative 4. You could leave it like that. You could write it as negative 2 3/2, or you could write it as negative 1.5. Those answers are all equivalent. And finally, on this last example, when we're doing the average rate of change in height between 2 to 5 years, make sure you remember, like, your years is going to be x's, your height is your y. Because think about it, I'm always giving you the x's that we're finding the average rate of change between. So here, when we have 2, we're at 35. When I'm at 5, I'm at 45. And then finally, you're just subtracting it. 45 minus 35 divided by 5 minus 2 is 10/3, which is the same as 3.3 repeating. I realize I went quickly through that, but I wanted to give you a brief overview and not take too much of your time so that you can complete the assignment for Monday. If you do have additional questions, feel free to come see me before or after school, and I'd be happy to talk to you more about average rate of change. Enjoy your weekend!